You can relate. Is Chamsadine here? Chamsadine? Davis? Gibbs? Yeah, that's it. All right. So let me. Oh my gosh. Screen. All right, so let me download. What kind of work? All right, so let's talk about chemistry. Let's have some fun with this. All right, so what is chemistry firstly? Right? So chemistry is that science which deals with, as you can see on the screen, the composition, structure, properties, and reaction of matter. And in particular, we are interested in how the different particles, molecules, atoms, ions, behave so as to explain all that we observe as far as the aforementioned composition, structure, and properties and reactions are concerned. So that's basically what chemistry is all about. And at the heart of chemistry is matter, right? What do we mean by that term? And you may want to write this down. Matter is anything that has mass and volume. Matter is anything that has mass and volume, right? So that is basically the focus of chemistry. Anything that has mass and volume is matter. So as I said before, we are concerned with, in chemistry, the composition of matter. So when we're talking about the composition, we're talking about the makeup. And in particular, to be more specific, we're talking about the different elements that make up a particular substance, all right? The other thing that we're concerned with is the structure of matter. And what does that mean? We're talking about how the different particles, atoms, ions, etc., how they're basically arranged so as to create the gross structure of the substance. We're also concerned with the properties. Now, in chemistry, this term properties basically mean the defining characteristics. So I'm talking about things like color, taste, density, and so on, right? All those different descriptors that you can observe. And also included would be the type of chemical reactions that substances will undergo. So collectively, all those things that we can observe are called the properties because we can use those to define and identify the different substances. And then finally, we're concerned with the reaction, right? And basically, we can look at the composition structure to basically explain the properties and the type of reactions that a particular substance will undergo. So pretty much, this is what chemistry is all about, even though things are a bit more complicated, especially when you go get to high level research. But fundamentally, this is what chemistry is all about. Okay, so this diagram here I like because, of course, I'm biased and I believe that chemistry is the most important science there is. Me and my colleagues from other sciences, we tend to banter back and forth in terms of whose field is more important, and more relevant and all that. And chemistry always wins the argument, always, without fail, right? And the main reason why is because chemistry is actually involved in other science disciplines, right? If you look at biology, if you look at physics, if you look at some things mentioned here, like medicine, toxicology, biochemistry, all of that, chemistry is involved somewhere, right? You cannot avoid it. And it is for that reason why most other scientific majors require some chemistry, right? If you're measuring, for example, in biology, you have to do chemistry, if I'm not mistaken, up to, if not organic, if not biochemistry, up to organic chemistry, right? If you're doing physics, you have to do at least, if I'm not mistaken, freshman chemistry. If you're doing nutrition, as my cousin did, and she would call me on the phone crying, please help me, problem. Chemistry is involved in nutrition as well, right? Chemistry is involved in pretty much all of the sciences. So chemistry is the most important science, as I said before, and the central science that affect all other scientific fields. And not only that, but chemistry also reaches into other non-scientific fields like law, like education, I guess, science is a subset of that. Business, what else do we have here? Well, I mentioned law already, but basically chemistry is involved also in other disciplines as well. So chemistry is the central science, and that's why it's important that depending on your scientific discipline, you're going to encounter chemistry in some form or fashion, right? Okay, so now we're going to take a bit of a detour and talk about the scientific method. This is a method that is used by scientists to make observation of a particular natural phenomenon, right? And that is true for basically all scientific fields, all right? So the scientific method is a stepwise method, and the first step in this method is we make an observation. So if you're studying something, whatever it is, right, you have to make an observation. This is where you're going to use your senses, right? Your eyes, ears, whatever, to make observations of whatever you're studying, all right? So that's the first step in this process. The next step is that you put forward a tentative, sort of speculative explanation for what you observed in the first step, right? So we call that the hypothesis, all right? So basically, you're kind of making a guess, but it has to make sense, right? You can't just put forward any arbitrary explanation. You have to put forward a reasonable explanation to explain what was observed in the first step, right? Of course, as scientists, we're not just satisfied with that. We want to know if this hypothesis is true. So in the natural sciences, chemistry, physics, and so on, we have to test the hypothesis. And the way we do so in the natural sciences is that we design an experiment or experiments, and then we conduct the experiment to see if the hypothesis is true. It's very important in terms of the experimental design because the experiment has to be designed in such a way to fail the hypothesis if the hypothesis is not true, all right? So basically, we have to perform an experiment. And this is where most of the hard work of the scientist comes into play, right? It takes time, it takes money, right? And equipment and all that. And you have to conduct your experiment and get information, usually in the form of data. So basically, what will happen, especially in the initial stages, is that when you get your data, you want to see if the data fit what the hypothesis that you put forward, it would fit it correctly, right? Initially, that's not the case, right? You'll find some misalignment between the data that is collected initially and the hypothesis. So what does that mean? That means that you have to go back to the hypothesis and either make changes to it, modify it, or replace it with another more reasonable hypothesis that fit the data, right? And then you do the next step again, which is experimentation to test the new hypothesis. And you repeat that process until you end up with a refined hypothesis that basically is in harmony with the data, right? When you end up with that situation, that refined hypothesis is now called a theory, right? It's a scientific theory. A scientific theory is basically an explanation that is backed by the weight of all the evidence that has been accumulated by the repeated refinement of your hypothesis by experimentation, all right? Another term that I need to talk about here is what is called a scientific law. A scientific law is basically a statement of what is observed. Usually we observe that after repeated testing as well, right? Basically, it's a statement of what is observed for which there are no exceptions. All right. So one example of this that you're going to meet later on in chapter 13 is Boyle's law. Let's see if I can write this down here. When we get to the chapter dealing with gases, you're going to learn about Boyle's law, right? And simply put, Boyle's law states that the pressure of a gas is inversely proportional to 1 over the volume, right? What that means, and I'm quite sure we can understand this, we have probably experienced this already. If you have a gas trapped in a container, right, and you reduce the volume, then the gas pressure will increase, right? So if you reduce the volume by half, the pressure will be double, right? If you reduce the volume by a third, the pressure will triple and so on, all right? And that is always observed in nature, right? That is an example of a law, right? One thing I need to emphasize here is that there's a difference between a law and the theory, right? The theory is an explanation for the law, which is backed by, as I said before, the weight of evidence that has been accumulated, right? The law is basically what is observed, all right? And it's very important that you understand the difference between the two, because I've even seen, major research scientists confuse the two when they're making discussions or talking about their experiments and so on, right? So that's the difference between the theory and the law. And also you need to understand the difference between the theory and the hypothesis, right? The hypothesis, as I said before, is a tentative explanation, right, before any experimentation, while the theory is the explanation that is backed by the data that is collected as a result of repeated experimentation, refinement of the hypothesis, and so on. Okay, so with that said, let me clear this here and move on to the next page. Okay, so what you're looking at here is a flow chart of what I've just described. All right. So as I said before, observation, right? What you use your senses to detect, and then you come up with an explanation, an hypothesis, right? And then you do your experimentation to test the hypothesis, right? And as I said before, if the data from here does not fall in line with the hypothesis, you have to come back up to here and you have to either make modifications to the hypothesis or come up with a new hypothesis. And then you do your testing by further experimentation and you repeat this back and forth until you get harmony between the data collected and your refined hypothesis. When that happens, you end up with your theory. All right. Now, one thing I did not mention earlier, which I'll mention now, is that even though you might have a theory, and let's say that the theory has been shown to be workable and accepted by the wider scientific community, it is possible that that theory is not the end of the story. Because you can have a scientist working in his lab or her lab and working on the same theory, testing it with further experimentation, and come up with data which actually conflicts with that theory, right? When that happens, what that means is that you have to go back up here and go through the same process again, right? You have to come back here, do some further experimentation, and come up with a new theory based on new data and so on, all right? And this is one of the good things about science, right? Is that basically there's no sacred cows where basically there's like a doctrine that you have to accept. You're free to question it, and if evidence comes up as a result of testing well-established theories, then basically the theory would have to be discarded and we have to come up with a new theory, all right? So that's basically how the scientific procedure works. And there are many instances in science history where this works. Now, my favorite example, which I'm going to talk about here, is a theory known as the vitalistic theory. Now, let me see if I can, let me see. I want something to write on. Okay, so I was talking about this with my previous class. I'm just going to undo. Open the book. Okay, so back in the day, and I don't remember when exactly, there was a theory that was widely accepted by the scientific community known as the vitalistic theory. All right? And basically what this theory says, right, is that there's certain compounds that exist in nature that we as human beings cannot make in the lab, right? Because according to this theory, there's a thing out there in nature known as a vitalistic force. And that vitalistic force was necessary to make these compounds, right? So that was the theory back then. And to be honest, you really can't blame people for believing that because nobody has been able to, successfully make naturally occurring compounds in a lab. Now, a guy by the name of Frederick Warner, and he was Swedish, and I think in Sweden, they put 2 dots over the O there. He was trying to make this compound. The name of this compound is ammonium cyanate, right? Ammonium cyanate, predictably, would be an ionic compound, right? So he conducted several experiments, step by step, until he got this compound in an aqueous solution, all right? Now, typically, if you have an ionic compound in an aqueous solution, what you would do in order to isolate it is that you'll heat the solution, drive the water off, and you'll be left with the product, the ionic compound, right? So that's basically what he was trying to do. So he heated this solution, but what happened instead was that instead of getting this compound in a solid state, a reaction took place which formed this compound, right? And the name of this compound is urea. Now, can anybody tell me here, where in nature can we find this compound?
Urine.
In the urine of mammals, human beings, cows, goats, dogs, whatever, right? And this was the first recorded instance of a naturally occurring compound that was actually synthesized in a lab. And this was purely by accident. He wasn't trying to make this compound, as I said before, he was trying to get the solid form of the ammonium cyanide, and instead a reaction took place which forms the urea, right? What that means is that this theory is now meaningless, right? That means that we can synthesize naturally occurring compounds in a lab. And that has been done ever since that day, all right? So this is just one example of how the scientific method works, right? You can have a well-established theory, right? Sometimes it's a situation where people did not have the tools to, delve into investigating the theory. In this particular case, it's quite by accident. In any case, once the theory has been contradicted, then basically at best, the theory would be a relic of the past, but we don't look at it anymore as explaining whatever we're trying to understand about a particular system, all right? So that's a good example, and there are many other examples I could delve into of how the scientific method works. Okay, so let me get back to the PowerPoint here. And there's something else I want to say about the scientific method, but we'll talk about that later on. I want to go into some definitions or just review or rehash some definitions that we talked about earlier, right? The hypothesis, remember, is a tentative explanation of what we observe, and that forms the basis for further experimentation. The theory is, on the other hand, a well-established hypothesis. In other words, the theory, a scientific theory, is established as a result of evidence, data, facts to support it, right? And very often, terms like theory mean something different in science as opposed to everyday language, right? If you talk to the average person who's a non-scientist and you're talking about, and you said to them that, I have a theory, then basically what it means in their mind is what we would call a hypothesis, right? But in scientific language, a theory is basically a well-established hypothesis which has data and facts to support it, all right? And then we get to the law, right? Which is basically a statement of what is observed. The law is not a theory. Let me say that again. The law is not the theory. There are two different things, right? The law is basically a statement of what is observed, for which there are no exceptions, while the theory is an explanation which is backed by the weight of data. all right? So please keep those definitions in mind, all right? And then I think the next slide is basically a side-by-side comparison between the theory and the hypothesis, right? So as you can see on the left side, the hypothesis is a tentative explanation, which forms the basis for further explanation and for further experimentation, while the theory is basically explanation, which is backed by facts and evidence and data, all right? Okay, so let's talk about everyday scientific thinking, because believe it or not, in your everyday activities, you have actually employed scientific approaches when it comes to solving certain problems that you face in life, all right? So I'm going to use this as an example. So let's say you want to play your favorite CD, right? Do you guys use CD players anymore? You say, okay, good, all right. So you can relate to this, right? So let's say you want to play your favorite CD, right? And you put your CD in your CD player and the sound skips, right? Okay, so you're annoyed, right? And you want to listen to your favorite music, right? So you have to come up with a solution to this particular problem, right? So the first step that I just mentioned, that's your observation in a scientific method. So what's the next step? Based on, you gotta be enough. What's the next step? Hypothesis, right? In other words, you have to come up with a reasonable explanation as to why the sound in your CD skip when you put it in your player. So let me hear what you think would be one possible reason why you make an observation.
The laser is dirty.
Okay, so something is wrong with the CD player. Is there another possible reason? Something is wrong with the CD, all right? So those are two possible hypotheses. Now let me see which one I have first. Okay, so something is wrong with the CD player, all right? So that's hypothesis one. So the next step in this process is what?
Experiment.
Experiment. So you have to test this hypothesis. So how would you test this particular hypothesis?
I would find out what's wrong with the CD player. So use a microfiber towel to clean the laser.
You could do that. Okay, I wasn't thinking about that. I was thinking something a bit more simple.
Use another CD.
What's that?
Use another CD.
Let's see. Right? So take another CD, put it in a player, and see if the same thing happens. Now, in this particular example, the sound is okay, right? So basically, we come to the conclusion theoretically that the player is functioning fine. So that's hypothesis one. What about hypothesis two, where something is wrong with the CD itself? So how would we test this particular hypothesis? Okay. Put another CD in, put the CD in another player. And in this particular case, the sound still skips. So therefore, the conclusion we can come to is that basically the CD has a defect. So this is just one simple example. And I'm quite sure you can think of others. Oh, this class starts at 11? Okay. I was hoping to get to a discussion shortly. Okay, you know what? I'm going to stop here. These are two links. You may want to look at these websites dealing with one important issue when it comes to the scientific method, your practice as scientist. I don't know how many of you plan to go into scientific research or whatever, but one of these, the last one especially, kind of very important. It talks about the consequences of scientific fraud. One example. The other one is where somebody published a paper and had to basically retract it because other people were trying to reproduce the results based on the method outlined in the paper, and they couldn't succeed, right? These are two examples of, again, how the scientific method works. And maybe I'll talk about them next time, all right? Okay, so that's it. So remember now, watch the videos, all right? And come prepared to ask questions, and we're going to work on the assignment, all right? So that's it. I'll see you guys next week. No problem. Take care. Yes, sir. Also, don't forget to turn in your the last page of your of the evidence of understanding page. Whoop, thank you, sir. Oh no, last it. Read that.
Wasn't sure if you watch Novelette at all.
Who?
Novelette. He's on YouTube. He does a lot of chemistry experiments.
Oh.
Uh,
I may have come across.
like turning like nylon gloves into grape soda and stuff like that.
Okay.
Yeah, no, it's like, you know, extremes.
No,
So I figured I might tell you because you might like it.
Send me an email, give that link.
Okay, yeah. Yeah, because
Thank you.
well, he goes into all the stuff too, you know.
All right.
Maybe I'll go.
Thank you.
Yeah.
Thank you, sir. Thank you, ma'am.
I watch a couple of chemistry things already. Some engineers too, like one of them's a retired engineer from NASA actually. So, is my field that I'm trying to go into is electrical engineering.
Oh, okay, cool. Well, that means you have to do chemistry, if I'm not mistaken.
Yeah.
Chemistry of what, Chem 1 or Chem 2?
I think Chem too.
Oh, really? Okay.
I think so. And
Okay.
I mean, too, like seeing what some of the people do too, were like, one of the engineers I was watching, they're trying to develop a new, communications, thing for NASA using, low power, low frequency, waves.
Oh, okay.
And, what is it?
You mean, this is, radiation, electromagnetic radiation, right?
Yeah,
Okay.
and, yeah, microwave waves. pretty
Oh,
much.
actually, okay.
And it's funny though, so because of it being different up in space on how it works, the low power, low frequency, high power. He can't really do like shows, like explain it like in physicality, I guess you would say, in person. So he kind of just needs to dumb it down. Using like just computers, because it's like
Oh, so he's like,
it's different physics up in space than, you know, down technically. Yeah,
he
so
kind of,
that's also interesting.
he kind of sounds like, one of my favorite scientists, you know, Neil deGrasse Tyson?
Yeah, yeah,
Yeah.
yeah. I've watched him
Yeah.
too.
Yeah, those guys are skilled in terms of explaining science to the common person.
Yeah.
And I must admit, I don't have that skill.
Well, I like to just because even in high school when I was in what is it, science class, I kept corrected because they were changing some theorems about some things, and I was like, hey, this is outdated. And he'd be like, please just let me teach the class from the textbook. I know it's outdated, but it's just this is what's required right now, you know.
Well, in my opinion, the role of a teacher is to keep on it.
Well, that's what he did.
Oh,
It's just though the coursework wouldn't let him
they wouldn't
teach
do-
it. No, because like Citrus Eye, at least they have the agreements with I forget what the book company is. And so pretty much until they release a new update,
Yeah.
that's what they have to do. I know, it's backwards.
I don't agree with that at all. I try, as much as possible.
Yeah,
I try to keep update with, because things change, science changes, like,
Yes.
so I mean, things that.
We had some books that were like 5 years old, and that's what